Well, I'm very excited to announce our next guest lecturer, Rajni Patel. During the last 20 years, his research has focused on robotic and mechatronic applications in minimally invasive surgery and therapy, haptics and teleoperation, surgical training and skills assessment, and recently on applications of robotics and haptics for neurological movement disorders. He has a huge career that spans 35 years, so I'm just encapsulating a small fraction of it. He's currently a distinguished university professor and Tier 1 Canada Research Chair in the Department of Electrical and Computer Engineering, with cross appointments in the Department of Surgery and the Department of Clinical Neurological Sciences at Western University. He's a founding member of CSTAR, the Canadian Surgical Technologies and Advanced Robotics, and also serves as its Director of Engineering. He's a Life Fellow of the IEEE and a Fellow of the ASME, the Royal Society of Canada, and the Canadian Academy of Engineering. He received his PhD in electrical engineering from the University of Cambridge in England. Welcome, Rajni.
Thank you very much, Kimberly.
Welcome, Rajni. I'll spend a minute adding a little bit to our students. Thank you very much for giving this lecture. I know you're very busy. I haven't seen you for a long time, although by emails, we have been exchanging emails, and it's great seeing you, Rajni. So for many years, I told some of you earlier today, Rajni was not arguably, was the first starting surgical robotics research in Canada, and one of the earliest internationally. So Rajni has been leading a great lab. I've been to his CSTAR. It's very unique in that one room, students do engineering work, developing technologies, and through one door, it's an animal surgical room. So it's very unique in terms of that. It's probably the best synergy you can find for surgical robotics, because most of us don't have that luxury of having both surgical room and engineering room, robotics lab connected together. That's very unique. So I congratulate Professor Patel for that. And I encourage you guys to visit him and his lab for the uniqueness you can feel once you're there. And Rajni received many, many awards. And I know recently he received IEEE Canada's most distinctive, best distinction, McNaughton Medal. Hugely deserved. So I will not spend more time telling more about Rajni, so you can go ahead to search and Google him on the internet, look at his papers, and his students are all over the world, professors all over the place. And so I give the floor back to Rajni, and I look forward to hearing you too, Rajni.
Thank you very much for the wonderful introduction. It's been a pleasure working with you and to give this talk. And I see that Haley is on the, we met before. Nice to see you again, virtually. Okay, so I guess I have about an hour, just over an hour or so for the talk, is that right? And hopefully if there are any questions, I'll be able to answer them at the end of the talk. Okay, thank you very much for the nice, wonderful introduction. Let me see if I can now start my presentation. Oops. Do I need to share the screen, or you can give me the right to share it? Okay.
Yeah, good. We can see now.
Can you all see the screen? Yeah. Okay, I'll try and minimize the. Okay, I think we can probably start. Can you see my full presentation, full screen? I'm just, because Zoom is a bit of an unknown territory for me at this point. I generally use Teams for most of my research. So are we okay?
Yes.
Yeah. Okay, so Basically, what I'm going to talk about today is what I had in the title, but it'll be somewhat broader than this in the sense that I'm kind of trying to give you a very broad overview of haptics and teleoperation, and to some extent guide you through the journey that I have had in coming to where I am today. And once again, my thanks to Professor Yu Sun and also to Kimberly for doing all the logistics and setting this all up. It's difficult to get an old dog like me to learn new tricks. I'm learning them now. Okay, so what I'm going to talk about is, well, before I do that, since Professor Sun mentioned C-Star, I'll give you a quick overview of C-Star. Maybe a couple of slides that can show you what we have, and to some extent also give you an idea of how we've got to where we are today. So C-Star was established over 20 years ago, primarily through funding from the federal and the provincial governments, and then there were quite a lot of private sector contributions. And it's located at University Hospital on the campus of Western University. And it's part of the Research Institute of the hospitals, both the London Health Sciences Centre and the St. Joseph's Healthcare in London. So there are three main areas of C-Star. One that I'm primarily involved in is the research side, and the research side has both engineering and clinical research. And then there's also the education and simulation-based training, which is part of the collaboration with the School of Medicine at Western. And some of the facilities that you can see here, we occupy 3 floors of one of the wings of the hospital, which is the extension to the hospital, which is called the Lindros Pavilion. And as you can see, we have a surgical lab, which is a very extensive lab with up to 8 fully working stations for surgery. We also have a surgical room for, which is lead line, where we can bring in imaging devices like the C-arm that's shown here. And there are facilities for giving talks. One of the advantages of the media room that is shown on the left is that we can connect to an operating room and see surgery being performed without actually going into the OR. And because of the way that surgery is done using robotics, we can actually project in 3D and see the surgery being, as the surgeon sees inside the patient, we'll be able to see it as well. And there are a number of facilities for simulation-based training. This one is kind of unique in the sense that it is for team training, so that a surgeon can create various scenarios and see how the team would react. And there, from my perspective, we have a lot of facilities in the engineering lab, and some of these are listed here. We have, at the moment, 3 Davinci systems in the lab. A recent acquisition is the Davinci ASI that that's just set up, and we are now trying to adapt it to some of the research that we are doing. We also have the Raven system, which is also a surgical robotic system, more for surgical research and training, but not really for patient use. And then we have a number of haptic devices and simulation facilities. So we are very well equipped for research in surgical robotics. Okay, so let me go back to the talk and give you an idea about what we have done so far in the area of teleoperation, haptics, and control. So this is the plan of my talk. What I'm going to cover is essentially the way that the direction of my research has taken since I switched to surgical and medical robotics from space robotics that I worked on up till about the beginning of this, about 2000, I guess, around 1999. And this, the layout here will show how my research has evolved and how we have progressed in various aspects of this work. The focus has been primarily on teleoperation. At some point, we brought in haptics into this, and though our interest is to look at various constraints under which we can use teleoperation and haptics in surgical or medical robotics. Now, one of the things that we've done over in the recent years, following the trend that we have now, instead of using the master-slave terminology, we started using the leader-follower or primary-secondary terminology to talk about teleoperated systems. Essentially, a system where there is, in the surgical case, there is a surgical console that is connected to the patient-side robot. In the conventional jargon, this should have been called master-slave, and I think because of the connotations involved, people have now switched on to leader-follower or primary-secondary. And as part of this talk, I'll also address a couple of applications that we have done a lot of work on, both in surgical robotics, and then more recently, we worked on neurological movement disorders. This is to some extent a result of our involvement in AGEWEL, the Network Centers of Excellence that is led from U of T. Okay, so let's start with teleoperated robotic systems. And I guess we are all familiar with this contribution by Canada to the space program. This is Canadarm1, and this is primarily a teleoperated system with a human in the loop. The robot, of course, is no longer used because we have now switched on to the second version of the Canadarm, which is shown here, which is a much more complicated version. And once again, it's teleoperated, but from inside the space station. You might recognize one of the astronauts that's shown in the figure on the picture on the right. If you're not, she was the Governor General of Canada until recently, and actually an alumna of U of T. She got a computer engineering degree from U of T. And I guess U of T shares the credit with McGill because she got an electrical engineering degree from McGill. So it'd be nice to see an astronaut who is an electrical or computer engineer sitting up there in space. The other person in the screen is an astronaut from Japan, and his name is Koichi Wakata. So once again, this is a teleoperated system. It's a fairly complex system because, as you can see, there are lots of degrees of freedom. Apart from the degrees of freedom where the arm is mounted on the space station, there are these booms that you can see here, which have also got several degrees of freedom. And then at the end of it, there is a part that is a dual arm system, which each arm is 7 degrees of freedom. So there's lots of degrees of freedom. And it was definitely important for a human to be involved in operating this. And this is one of the latest versions of NASA's contribution to space. This is the Perseverance rover that is currently sitting on Mars. And it's kind of an exaggeration to say this is a teleoperated system because of the time delays for the signals to reach Mars. It's about between 4 minutes and 24 minutes. But currently, and obviously it depends on the location of Mars and Earth in their orbits, but currently the time delay is about 14 minutes. So teleoperating this system, as you'll see, is probably not a realistic thing to do. Anyway, with that brief introduction, let me move on to robotics and surgery. Now, the robots that were used initially were this Zeus system. And at C-Star, we had 2 of these. In fact, one of them was used for the world's first beating heart coronary artery bypass grafting using a surgical robot. And this was done by cardiac surgeon Douglas Boyd, who is now at the University of California in San Francisco. Now, this is obviously on the left-hand side, we have the robot is a patient-side robot which has laparoscopic instruments that are introduced into the body through small incisions about 1 centimeter across. And this is controlled from the surgeon's console on the right. This console gets a video image from a camera that's also inserted into the body through one of the incisions. Now, this was a pretty well-designed system. One of the things about this system was that it actually came from funding provided by NASA to this company called Computer Motion. And the result of that was this Zeus system, which was then commercialized. Now, this system was also used to test telesurgery. In fact, the first telesurgery case was an experimental work that was done to do surgery in New York by connecting to Strasbourg in France. And they did a fairly simple surgical procedure, which is gallbladder removal, called cystectomy. But it was a demonstration to show that this could be done, and also in the presence of time delays. This was a dedicated connection set up just for this purpose. And at C-Star, we also did a lot of work in telesurgery, primarily to see how effective it would be to provide surgical treatment to patients in Canada's more remote areas. And then we set up, with the help of Telsat and Bell, dedicated connections, using VPN and satellite connections to connect a patient, the surgeon's console on one side, all the way up to Halifax, and then back to the patient-side robot sitting in the next room, a distance of about 3,000 kilometers round trip. And we did a number of tests to evaluate which of these was more effective, etc. And there were a number of problems with doing surgical robotics or telesurgery. And a more definitive case was shown by doing telesurgery using the next version of surgical robot, which was that developed by Intuitive Surgical. Incidentally, the company Computer Motion and Intuitive Surgical had a bit of a problem, and the legal case that came out of it, Computer Motion ended up losing, and so they were bought over by Intuitive Surgical, and their robot was put in storage. So now what we have, which is this robot called the Davinci, which is a very it's probably the most commonly used surgical robot currently in the world. We had a collaboration with Intuitive Surgical where we set up a telesurgery type environment to evaluate the use of the Davinci system for telesurgery. And once again, we used the setup that was prepared for us by Telsat and Bell Canada. And that allowed us to evaluate the performance of a particular surgical procedure using the Davinci telesurgery capable setup. And the results are primarily shown here for a particular surgical procedure called Pyloplasty, which is to remove a blockage in the ureter that connects the kidneys to the bladder. And as you can see here, while this surgery was possible, there was a substantial time delay involved, going up to about 350 milliseconds. On the average with the VPN, it was about 60 to 100 milliseconds. While the surgery was possible, what the surgeon said was that they had to slow down their procedure to compensate for the time delays. And the result of all of this was that this kind of surgery was very tiring. And Intuitive Surgical decided that this was not really a feasible thing to do. Of course, there were these issues of legal issues involved as well in terms of who takes the blame if the network goes down. Anyway, so primarily this was put aside. But the thing was that it has been worked on and demonstrated, and there has been work by others to demonstrate telesurgery. One of the cases was from one of the Canadian surgeons doing surgery from a submarine out into an operating room on the ground. Okay, so as I said, the time delays were quite significant, and at that point in time, this was set aside. But one of the things that is possible, and this is something that I should mention, is that the current developments and interest in AI and autonomy in surgical robotics may bring this telesurgical applications once again into the limelight. So there are people still interested. In fact, I had a visit recently from the Japanese group working in telesurgery, or working in surgery on the space station, and they were interested in exploring telesurgery once again. So there are possibilities that this can be brought back again. Anyway, so let's now go into surgery in the lab and in the OR here and on Earth. Now, at C-STAR, as I mentioned, we've recently got a Davinci Si system for research purposes. And this is an interesting system because it's a dual console system. So there are two surgeons who can connect to the robot. This is designed primarily for training. But there have been several other versions of the Davinci. I think we are now in the 4th or the 5th generation of the system. And some of the instruments and the capabilities are mentioned here. There have been also other surgical robotic systems, both for research and commercial. And I'll just go through a few of these. In fact, the ones that are shown here are some that are commercialized, some that are also used in research. And some that have resulted in commercial systems from research in developing surgical robotics. So these are a few systems in Europe and in the US. And these are two Canadian systems. The one on the top is a system developed, I think the version that is the latest version, is developed by Titan Medical, that was founded by one of the surgeons from C-STAR. And the one below it is the NeuroArm version that was created at Calgary with the help of the Canadian Canadian robotics company that worked in space robotics, MDA. This is now the bottom figure. This is a NeuroArm, which is now actually being commercialized through the US by a company called Deerfield Imaging. Okay, so with that introduction to surgical robotics and the commercial parts of surgical robotics, let's now go on to the research side, which is haptics and teleoperation. By haptics, I mean the sense of touch, there's tactile sensing, as well as force reflection. One of the first papers in the area of teleoperation and haptics was a paper published by a group from Italy at the University of Pisa, led by Paolo Dario, one of the major contributors in the area of medical robotics and surgical robotics for a very long time. And there have been a number of people who have worked in this area. And some of the key players are mentioned in the publications list here. And several of the contributions were from my group, my doctoral students, such as Tavakoli, Curry, Talasas, and others. So there's been a lot of work in the area, and we have contributed a major amount of that as well. So the need for haptics, I mean, in the early days of teleoperation, people didn't really think very much about introducing haptics, but there has been an interest in introducing haptics from surgeons who are involved in doing robotic surgery. And this was highlighted in a report that was published by the FDA in the US that evaluated the Davinci surgical system and its application for teleoperated robotics. And the main point about haptics, as far as this report is concerned, is that the surgeons all felt that haptics or tactile feedback was necessary to determine the condition of tissues and the contact that they make with tissues during surgery, and especially in suturing. So primarily the need was to obtain accurate and reliable measurements of tool tissue interactions. Now, in terms of introducing haptics in surgery, the question arises, how do you actually get the measurements of forces or contact that you need? And there are some major challenges here. Now, I've listed the 4 of the most important ones here. These are and I'll go through each of them in detail. So first we'll look at the location of sensors. And this is an interesting problem because if you look at minimally invasive surgery, that is surgery that's done by inserting instruments through small incisions in the body, through the incisions would have an attachment there, which would be called a trocar, and through which the instrument would be inserted. Now, this figure shows the level of forces that are measurable at various points. So if you look at the instrument here, I've shown a handheld laparoscopic instrument, but the same would apply to a robotic instrument. So you can see that the forces outside of the body are of the order of about 2 to 6 times greater than the force at the tip. And so that means that if you put a force sensor outside the body, it would not really be very meaningful in obtaining an accurate representation of the interaction forces inside the body. So basically what this says is that you want to put force sensors as close to the tip of the instrument or as close to where the tool tissue interaction is taking place as possible. And that raises a number of other issues, which are the challenges listed here. That is, you have to make the sensor small enough to be mounted near the tip of the instrument. It should be sterilizable, biocompatible, and of course, the cost of it is also important. One of the things to remember is that the instruments that are used on the Davinci surgical robot are quite expensive. Each of them costs about $2,000 a piece. And they can only be used about 10 times. And so they have to be sterilizable. So these are important issues. So the question of designing sensors is something that we also looked at. Now, there was some very interesting and impressive work that was done by a group from DLR, the German Space Agency, that also does work in surgical robotics and, in fact, robotics in general. And they built a very nice and compact strain gauge-based sensor that could be mounted at the tip of the instrument. And this is shown here. And we used strain gauges to sensorize the Davinci instruments that we used for our work. We also sensorized handheld laparoscopic instruments to demonstrate the effectiveness. And this is shown as part of a student project that was done at CSTAR. And more details of the sensorization process are given in the paper that's listed at the bottom of the slide. Now, we use this approach to sensorize the Davinci instruments, and which we mounted on a test bed that we created at C-Star with two robot arms. And I'll talk about this test bed a little later on. But the thing about this was that we could sensorize the Davinci instruments and mount them on surgical robots. And this allowed us to implement haptics in this particular test bed. This was part of a doctoral thesis researches at C-Star. The group at the DLR did also some work on optical force sensing, which in my opinion is probably much better suited for surgical robotics than strain gauges. And this is something that they used, and we kind of followed the trend that they set and implemented fiber Bragg rating and optical force sensing on the Davinci instruments. This was part of a collaboration that we did with Johns Hopkins and Russ Taylor's group at Johns Hopkins, where we prepared a grasper for the Davinci instruments and sensorized it using fiber Bragg rating. And though basically this is a nice, very compact design in the sense that all you really need is to have a wire coming out that allows the sensorized part to be plugged into an interrogator to process the data from the fiber, from the FVG sensors. Now, to move on to some of the other issues, especially issues related to controls, there are two major requirements for teleoperation and haptics. The two are transparency and stability. Transparency is how well the follower environment is represented to the user or the leader. That is, how transparent is the environment so that the user feels that they are interacting directly with the environment, that's the body, and not going through a robot. And the stability part, in a sense, arises because of the need for transparency. The two are actually contradictory requirements. So there is a trade-off. In order to make a system transparent, we have to make the system less sluggish and, in a sense, compromise on stability. And if you try to make the system more stable, that reduces transparency. So there is a compromise between the two that has to be reached. And this is one of the major limitations of haptics in teleoperation. You can get a good, very reliable system, but this haptics would not be as good. And stability issues that arise in teleoperation in general and with haptics-based teleoperation are also difficult to address. There is, of course, time delay in the system, as we saw in the telesurgery case. And the time delay could be due to communications, but it can also be due to the third part here, the flexibility in the mechanisms. So the time delay is one issue, which can, as you know, in control systems, if you have time delays in the system can become unstable. There's also the question of non-passivity of the environment that the robot comes in contact with. In particular, in the human body, you have respiratory motion and cardiac motion. And both of those can inject energy into the system, which is what makes the system non-passive. So let's look at these issues individually. So for stability and transparency, we're going to have a trade-off, and there's a lot of work that was done in this area, primarily by people who've looked at teleoperation and haptics. And some of the major contributions are listed here. Primarily work from Tim Salkudian and his group at UBC, and Hashurizad and his group at Queens. And there's the major work, the initial work was done by Lawrence in the US. Now, to understand the stability problem, let's look at time delays. Now, if you have a unilateral system, that is, you provide a position input into the system, which then activates something at the follower side. Now, but if you don't close the loop, that is, you don't get the result back and sent back to the user, this is just unilateral. So it's only in one direction. Now, if each of the devices, like at the leader side, the device is stable, and at the follower side, the device is stable, then this overall system will be stable. And even if there are time delays, that would not have an effect on the system in terms of stability. But when you close the loop and you have a feedback coming from the environment back to the user, so if you have a position input that is provided by the user through a device such as the one shown here, which is a haptic device, and the result is that there is a force that's generated at the follower side, and that is sent back as force to the haptic device, then that is closing the loop. And the user then reacts to the force and changes the motion. So this thing can be a problem, can create a problem because of time delays. So this setup is a bilateral system. And this is a haptics-based bilateral system in the sense that force is reflected back. And that this system has a potential for instability. So in the second part, which is the non-passive behavior, as I mentioned, a system would be passive if there's no energy injected into the system. But when you're dealing with organs in the body which undergo respiratory or cardiac motion, then that injects energy into the system. And this can also result in stability depending on how sensitive the system is or how stable the environment is, the overall system is. And there are various theorems in stability theorems for teleoperated systems, for interconnected systems, which rely on this result of the small gain theorem developed by George Zames at McGill. Now, the idea of flexibility is also important when we're dealing with teleoperated robotic systems. And the flexibility is primarily of two types. Your joint flexibility, there's flexibility in each of the joints of the robot. This could be when the robots are cable driven, or there is flexing in the robots. And so that is also an issue. But the part that is of perhaps more interest for surgical robotics is the flexibility in the body of the robot or in the instruments that the robot is holding. So if the robot has a long, slender instrument, that instrument can possibly flex. And that creates difficulties in terms of stability. The other thing is that if a robot is used to manipulate an instrument such as a catheter, which is very flexible, that can create difficulties. The flexing in the catheter, in a sense, indirectly results in time delays. And similarly, there is a lot of work being done recently, in fact, at U of T as well, on concentric tube robots. Now, those are robots with flexible tubes, and those can also create stability issues. And there has been a lot of work that has been done to address this idea of flexing in various links of a robot or instruments that are carried by a robot. And some of the, and one of the ones that's particularly related to stability in surgical robotics is the paper by Tavakoli and Howe, which was work done at Harvard. And this showed that there are issues of haptics that need to be addressed when there is flexibility in the instruments or mounted on the surgical robot. And other papers by my group had addressed the general problem of flexibility of any instrument carried by a surgical robot or by any kind of robot. So this is just something that we did in the lab to show how flexibility can result in instability. So this is part of the actual result from a flexible link that was added to a robot. One of the things that we also explored, and this is because of our interaction with clinicians at C-STAR, was to show how haptic sensation can be helpful to a surgeon. And in what way should this information be presented to the surgeon? So providing feedback directly to the surgeon through a haptic device so that they feel the force of interaction is the ideal way of doing it, but it's not necessarily the only way of doing it. We can provide force information in other sensing, but in other representations, such as showing them as some bar graph that the surgeon can use and superimpose the graph on the actual visual image that the surgeon sees. So in order to demonstrate this to the surgeons, we looked at two specific examples, primarily because of the surgeons who were involved in the work that we did. So one of the surgeons was a thoracic surgeon, and his interest obviously was primarily in lung cancer resection. Now, one of the things that arises during lung cancer resection is that the lung that has the tumor is deflated. So the preoperative image and the intraoperative imaging do not quite match precisely. And so the surgeon relies quite a lot on the feel in open surgery to feel where the tumors are and to kind of map that to the actual preoperative image, the CT image. So the intention was to see if we could create a laparoscopic instrument that will allow the surgeon to minimally invasively palpate tumors in the lung. The other part that we were interested in was suturing. Here, the interest was in suturing, especially from the surgeon who was interested in doing cardiac surgery. And in this particular case, they were interested in mitral valve repair. So before I talk about this, let me just talk about some of the setup that we created in the lab at C-STAR to allow us to do this investigation. So I'll take a few minutes to go through some of this test beds that we created. So the test bed basically tried to create a leader-follower setup where the leader was a haptic one, the haptic device, which was a haptic one from Kwanzaa, and which we enhanced into a 7-DOF system. And there was visual feedback provided through head-mounted displays. And there was also the possibility of showing on that head-mounted display a bar graph of the force that was reflected. And the follower was an industrial robot that we used, for which we bypassed its controller and set up our own control environment, primarily so that we could change the robot in any way we wanted or we needed to change because of the particular application we were interested in. And this was mounted with, in the case of tumor localization, mounted with a tactile sensor that we created in the lab with a 15x4 array of capacitive sensors. And we also mounted a force-torque sensor on the robot to measure 6 degrees of freedom, force and 6 degrees of freedom. This setup is the one shown here. Basically, it's one robot with a tactile sensor mounted on it. And the instrument is designed to be minimally invasively inserted into the body. And at the leader side, we had a haptic device that was used to manipulate the robot and actually also feel the force that, or the pressure of the force that was reflected by the interaction between the tactile instrument and the phantom sample. In this case, it was the liver. Okay. Let me also talk about a second system that we created, which was very consistent. Sorry, I think, yeah, this is a two-robot system where we created an environment where we could do suturing, so we needed a two-handed operation. So here there were two surgical robots, both mounted with Davinci instruments, which were sensorized for force sensing. And there were two haptic devices, two haptic wands that were used to manipulate the two surgical robots, the two PA-10 surgical robots. So the follower had two surgical robots, the leader had two haptic devices. And once again, there was, and also on this one, we had the camera was mounted on a separate robot, which was the ESOP robot from Zeus that we still had in the lab. So this could also be manipulated from the haptic one, from the computer that controlled the leader part of the system. And the system is shown here. So this is a fully dual-arm, teleoperated, haptics-enabled system. And this is the test bed that we created in the lab to explore the use of haptics in teleoperation. Okay, just to show you the modifications that were done to on the leader side, the haptic device was initially a 5 degrees of freedom device, and this was changed to 7 degrees of freedom with appropriate modifications. And we also, one of the modifications was that we could also provide grasping force, which was not possible with the system that we purchased. And on the follower side, the instrument that's shown at the bottom here is the tactile sensing instrument, which had 15x4 array of capacitive sensors. And the one above is the instrument, which is the Davinci instrument, which was sensorized. In this case, what's shown is the sensorization with strain gauges. But what we have done more recently is using fiber Bragg rating. Now, one of the things that we also did with this test bed was to create a remote center of motion. If you recall, the instruments are inserted into the body through small incisions so that when the surgeon manipulates the instruments are pivoted about the point of entry. This means that we have to create a pivoted point at the entry of or what would be the entry to the body. And this is done through what is called a remote center of motion. So essentially, this is generated through software. In other words, the robot is programmed so that it rotates about a particular point. So we can move this point up or down the axis of the instrument. But once we set it, that's the point at which we assume the instrument is been inserted into the body. So it has been pivoted about the body. So this, in a sense, makes it more realistic when we try to palpate or to do suturing with this setup that we created. So each robot has a remote center of motion, which is programmed in software. So there were several applications that we looked at, and I've listed 3 here, and I'm going to talk about 2 of them. The third one here is somewhat different because that was used for training, but I'm going to talk about the 2 which were done using the setups that we created, the in-lab experimental test beds that we created. Okay, so let's first look at the palpation issue. This robotic-assisted palpation using tactile sensing. The tactile sensors on the instruments allow us to determine areas of higher stiffness, or to distinguish areas of higher stiffness from those of lower stiffness. The plot on the bottom, or the figure on the bottom, shows in pink or in red the areas that have higher stiffness compared to the surrounding area. So the yellow is less stiff, and the green is even less stiffness. And the blue is relatively no stiffness measure. One of the other things that we noted in doing these experiments was that the tactile sensor has to be applied to the tissue in a particular way in order to maintain consistent and reliable exploration of the surface, and to get meaningful and repeatable motions. And if you think about it, the way that we humans do touch with our fingers is that we adjust the fingers to, once we see what kind of feel we have at the fingers. And in a sense, this is doing something similar. So the robot is then been programmed to palpate tissue in the particular way, depending on what kind of feedback or force feedback that it is receiving. And the other point that we also addressed was, how do you combine the force that is felt by the robot and the tactile feedback that is sent to the robot and to the user. So we did this in several different ways. The first was just a visual presentation of tactile feedback. That is, we showed the pressure map to the user. Then we had a combination of that pressure map and reflection of the force to the user directly to the haptic device. And the third was to show the pressure map and a visual representation of the force that was exerted by the user on the tissue being palpated. So these are denoted by these acronyms: VPTF, DRFF, and VPFF. And this was done in a fairly systematic manner using the test bed with bovine liver, and on which modules were embedded to represent tumors. And 8 subjects did experiments with this setup in a teleoperated manner, and palpated the liver. And we also did experiments on lung tissue as well, using this single arm setup. And this was also done with a remote center of motion. So the question then was, what is the best way of representing the result to the clinician, to the surgeon? But in general, all of the approaches that we used gave a significant decrease in the maximum force that was applied in palpation. And it also increased the tumor detection accuracy significantly. So the results in general were positive, and I think the surgeons were generally very happy about how this could be done. The main idea really was, how do you implement this in an actual surgical setup using, say, the Davinci? Here I've shown a comparison of the results that were obtained for both small tumors and large tumors. By small, I mean tumors of around 5 millimeters in diameter, and large were about 10 millimeters and larger. And as you can see, a combination of the visual representation of force and visual representation of the pressure map generally gave a better result, primarily because the accuracy was significantly higher when we represented the information, especially from the force sensor, as a bar chart. Higher than compared to reflecting it directly to the user. And obviously, there is this whole idea of what is the least noticeable force difference that one feels, which may be a significantly higher amount than the change taking place in, say, measured due to the ATI force sensor. And this shows a comparison of the various results of the various tests that were done. I won't go into the details of this, but as you can see, the visual representation of force generally gave a much better accuracy than direct force. And one of the things that we also, as I said, we also did was to see if the robot would be able to do some of this palpation semi-autonomously. And we created an environment where, depending on the force that was applied, the robot would react in deciding which area of the tissue to palpate, and to concentrate more on the area where there is a larger variation in stiffness, because that would then denote the margin of the tumor. And so this was something that was possible to do through a robot. Now, this is work that one of my students is now extending to put AI in the system. So with all of the developments in AI, this could be done using machine learning and coupling that with the robot. This figure shows that this particular, creating this level of autonomy compared with the force sensing and pressure sensing, we were able to get an accuracy of about 93% in tumor localization, and reduce the amount of force that was applied to about 3.4 newtons, and restrict the force that was maximum force applied to not more than 6 newtons. Controlling the amount of force that's applied to tissue is important, because especially when tissue such as lung is very soft, there is the danger of damaging tissue if you palpate too fiercely, too heavily. Okay, so as I said, we were able to get a better control over the applied force, and because of the robotic nature of the work, we were able to create a consistent and repeatable performance, so that any part of this could be repeated by the user at any instant in time. An extension of this work was to see how we can do the same thing on a Davinci instrument, on a Davinci system. So one of the students developed one of the laparoscopic devices for the Davinci, on which we mounted a tactile sensor on one side and an ultrasound transducer on the other side. The tactile sensor was created in the lab, and it's relatively inexpensively. But the ultrasound transducer was one purchased off the shelf from an ultrasound imaging company. So this is the tactile sensor. It can be very easily mounted on the instrument. And on the other side, there is the ultrasound transducer. So when this instrument is inserted into the body, it can palpate tissue, and it can at the same time also, with the same instrument, by simply flipping the instrument, the part of the instrument around, it can do ultrasound imaging of the tissue. And then the pressure map and the ultrasound image can then be integrated to provide a much better view of the tactile sensor. This can also provide depth information of the tumor because of the ultrasound imaging information. Here, the test is being done using a liver sample. Okay. So let's look at the next application, which is suturing. And here, the task is fairly complex in the sense that it requires a two-arm operation. Because the task of suturing is a fairly complex task. And from the people that I've observed in my own work on it, I think it's a very difficult task to learn because it requires a control of force and movement at the same time. And then at the same time, you are using instruments, controlling instruments remotely without actually, if you are not feeling the force that's reflected back to you, then the work is even more difficult. So force reflection is particularly useful here. And of course, there are certain requirements in suturing. That is, we would like to ensure that the knots are tight enough so that they don't become loose, or that there's not too much force applied, or when the knots can break. I've seen also that sometimes novices tend to drop the needle so because of insufficient force applied to hold the needle. And misjudging, for instance, misjudging the amount of force required to insert the needle into tissue. One of the things that we have observed over the years in doing this work in suturing with force sensing is that by looking at the force profile of the user when they're doing suturing, we can tell fairly easily how proficient they are in suturing. And we have some results and some papers that we published on using this information for training novices in suturing, where they can emulate an expert surgeon and by looking at the forces that are applied. Anyway, going back to the task here, we divided the task into a number of subtasks, which are listed here. That is, grasping the needle and positioning at the right place, inserting the needle into tissue, pulling the needle through the tissue, looping the thread, grasping the thread, and tying the knot. So these are all the tasks that are required in doing one particular suture. So here is a video with one of the doctoral students who also was a cardiac surgery resident doing suturing, and this was part of her research project for her PhD. What she's suturing is a mitral valve annulus on a pig's heart. This is just one illustration of one particular suture that she did. So here she's pulling the thread and then tying the knot. So it's grasping the suture end. And you can see the process is not very easy to do, especially with the laparoscopic instruments, in this case, surgical robotic instruments. The surgeons who have been doing this for a while, they did this much faster than this. And the student got much better as the project went along. She finished her PhD and is now working an assistant professor at Stanford. Okay, so in our evaluation, we compared suturing using robotic system in 3 ways. First, without force feedback, then with visual force feedback, and then with direct force feedback to the subject's hand. And we examined the 6 parameters that we considered, that is quality of knots, task completion time, force consistency, tissue damage, amount of tightening force, and the control of the instrument by the user. This was evaluated with several residents and expert cardiac surgeons. And this figure here shows the time taken to complete the task, which basically did not change very much depending on whether there was feedback or no feedback. There was force feedback or no force feedback. This shows the force applied during suturing. It's inserting the needle. And you can see that with no force feedback, the amount of force applied was significantly higher. And this shows the forces applied in knot time. Once again, with no force feedback, the amount of force applied in tying a knot was significantly higher. The interesting thing here is that the visual representation of force, in addition to direct force feedback, actually reduced the force. This was because the visual representation of force provided much more accurate force measure through the bar chart that was overlaid on the visual image that the user saw in their head-mounted display. Okay, so it turned out that visual force feedback actually gave the best results for the quality of the knots and tying the knots. And the combination of direct force feedback and visual force feedback gave the best overall performance. And as I mentioned, the use of force feedback to the user is particularly useful in training. And we have used this by creating a training environment for residents and novices when they want to learn suturing, both for handheld laparoscopic instruments as well as robotic assisted. But the important thing about providing force feedback and haptics is that the forces applied are generally much more consistent and significantly lower. So this is a slide that I'm putting in here just to kind of give you a quick idea of what people are looking at. Because much of what I talked about hasn't brought in any autonomy in the system. And some of the work that a couple of my students are doing now is to try and see how autonomous we can make, say, palpation and to some extent suturing. So this is a report that came out after a meeting that was held in the US, where people were looking into the future to see what kind of issues that would arise in terms of autonomy. At this point, much of surgical robotics is really at level 0 and to some extent level 1. What we are aiming for currently is level 2 to create task autonomy. So maybe even create a task like palpation to do it autonomously, or to do some parts of suturing autonomously, like tying a knot, for instance. So a surgeon, for instance, would insert the needle, pull the thread out, and then tell the robot to tie the knot. So that could be, to some extent, an autonomous task. The others are obviously significantly farther in the future. Let me now move on to another topic. This is work that we did somewhat more recently, maybe in the last 8 to 10 years, which is to do with movement disorders. The work that we have done has been to explore the use of robotics, in particular telerobotics, in one particular application, that is rehabilitation following a stroke. And much of this work was actually funded through the Agewell Network of Centers of Excellence and also through specialized funding that we got to build certain devices. The idea is to use a robot that can, to some extent, learn the therapist skills, but also provide haptic information that can be used to measure the progress made by a person with stroke in their therapy. And the third part, which is perhaps much more relevant today, is to create a remote tele-robotic rehabilitation environment so that much of the rehabilitation can be done in home, which is particularly useful in this time of the pandemic. So the tele-robotic setup that we have is a 2DOF device on the patient side, which is a haptic device that was also built by Kwanzaa. And on the therapist side was another haptic device that we used, which was also built by Kwanzaa. And both of these haptic devices are capable of large amounts of force, so that we could provide rehabilitation training for a significantly large force exertion on the part of the patient. Now, this was coupled with a VR software environment, essentially a gaming environment that we created. What we've got at the moment is a 3D gaming environment that has just been created by a few of software engineering students in a project. And this allowed us to create a setup that is shown here, where on the patient side, we would have the leader robot, and on the therapist side, we would have the follower robot, so that the therapist could then reflect different amounts of force and see how the leader or the patient would react. We have also built a lower limb device that we have been evaluating, and we were about to go into evaluating the patients when the pandemic broke and everything was put on hold. So there is a lower limb device as well. So these videos show the upper and the lower limb. So the upper limb device is being used for both in assistive and resistive modes. On the left, what the therapist is doing is assisting the user by providing or guiding the user to move to different targets. So there's assistance being applied. So this would be perhaps in the initial stages of the therapy. On the right, the therapist is actually resisting the motion of the patient by requiring the patient to exert more and more force. So demanding the patient put in more effort in completing the task. So both assistive and resistive motions are possible with this setup. And one of the advantages of this is that all of this can be recorded and replayed and can be used to analyze the performance of the patient or the progression of the patient in their therapy. Here we've shown both the patient side robot and the therapy side robot in the same view, but the therapist side robot can be located in the clinic and the patient side robot can be located at home. And all of this could be done remotely. The other advantage of this, and this is something that we have also tried, is to have the therapist work with several patients at the same time, so long as the bandwidth of the internet is sufficiently high. So this is also possible. Anyway, so we have also modified these robots, especially the patient side robot, and put in safety features in there so that this could be used in home. Because that particular haptic device or the robot is capable of large forces, safety is of course of primary importance here. So we have put in safety features in there which would stop the robot completely if there was any danger whatsoever. Now, the other aspect of this, I mean, I've listed some of the key features here. The other aspect of this is that because it can be used remotely, of course, it's well suited for performing this kind of rehabilitation therapy in home. But one of the things that can be done is that by recording or observing how the therapist uses the therapist side of the therapist robot, we can create an environment that can use machine learning to learn the motions or the ways the therapist reacts. In a sense, create an intelligent virtual therapist. So this would be done through, say, learning from demonstration of the therapist. So that way, we can have a robot that can act in place of the therapist and monitor the patient as the patient is going through the exercises. So this is an ideal application of machine learning in AI. The second application that I want to talk about that we looked at in neurological movement disorders is something called focal hand dystonia. This is not so much a tele-robotic or teleoperation kind of application as a haptic application. Now, writer's cramp or focal hand dystonia is something that is not very common, but this is something that the neurologist that we worked with was particularly interested in examining. And so writer's cramp is a form of task-specific focal hand dystonia. It's focal in the sense that it's restricted to a particular region, and task-specific because it's restricted to a particular task. In the case that we're looking at, the task is writing or playing an instrument. So it's a neurological condition that affects a muscle or group of muscles in a specific part of the body and causing sort of involuntary muscle contractions or cramps, and also results in abnormal posture in performing these tasks. For example, in writing, the fingers could either curve into the palm or they could extend outward and without control. So the nature of the problem is not fully understood yet, but there is a treatment that tends to work, which is a treatment provided through botulinum toxin injections. So in our work, what we wanted to do was to explore the effect of haptic feedback on cramping. So the question was, how can haptic feedback reduce the amount of cramp that a person suffers from? So by using haptic feedback, can we reduce the onset of cramping? We also looked at the idea of sensory motor integration, whether haptics and vision together or either of them could help the user to address these. So this is the experimental setup where we created a force reflecting plate that will allow the user to feel haptic feedback when they are writing on a surface. And we create a sensorized pen that could measure the grip force that the patient uses during writing. So this device here is a haptic device that can measure the forces reflected and reflect them back to the grip. Okay, so the experiments that we did was normal writing when the patient writes without any sensory manipulation. And then we did robotic-assisted writing, and a haptic device supports the pen and provides a compliant writing surface. So depending on the amount of force that exerted, the surface provides compliance. So this, in a sense, manipulates the kinesthetic and haptic input. We also did a test where the user was blindfolded to see if that made a difference in their writing ability or the onset of cramp. The idea really was to understand this whole issue of sensory motor integration and how that affects this particular movement disorder. So as I mentioned, the chemical treatment, which is the botulinum toxin injection, is effective to some extent, but not in all cases. And what you've done here is to compare various patients. There were several patients that participated in this study, something like about more than 20. But what I'm showing here are some of the typical results. So these are participants 1, 3, and 4. And the results are for injections and injection plus the haptics. And you can see that there's a significant or noticeable improvement with the haptic setup, where there is a force reflection that adjusts the writing surface. Okay, so let me now conclude this talk by talking a little bit, by giving you the overall results of what we have done so far. So in our work, we have shown the importance of haptics and force reflection in surgical robotics, especially in certain tasks. This issue can be particularly significant when there is variation in forces, especially when you're using surgical instruments, instruments such as catheters and needles, which are flexible. So that is a major importance in terms of how you implement haptics and force reflection. There are two particular applications that we considered, palpation and suturing, for which it's very clear that there is a direct need for haptics and teleoperation, and there's a definite advantage for doing this minimally invasively. If you have these two features available. In the case of rehabilitation and stroke, there is a clear need for teleoperation and haptics. And because of the way that this can be implemented, there is a possibility of more direct application of AI and machine learning, and possibly the use remotely so that in-home therapy is possible. And the issues that arise from haptics and teleoperation, which are important to consider and which have been addressed, but the solution actually requires much more work. The issues of stability, time dependence, latency, and efficiency and transparency. There are issues that need to be addressed, especially through some of the developments in machine learning and AI, which can address some of the issues with the time delays, for example. And I've talked about some of the issues here. Finally, before I close, just a list of some of the large number of people that have participated in this work. And there is an ongoing work as well. Many of the people who participated are medical people, clinicians and residents and clinical fellows. There are also a number of students who came as master's or PhD students who have gone on to do MDs or gone on to work in the medical field. And the people who pay the bills, both NSERC, CIHR, CFI, and AgeWell. And thank you very much. And I'll be happy to answer any questions that you may have.
Thank you, Rajni, for the wonderful talk. It's very technical. I think that's what our students need. So our students, questions.
I have a question. Thank you very much for your talk. I understand you differentiated between force sensor and tactile, force feedback and tactile feedback. If I'm correct, tactile feedback is mostly for sensing the consistency of the tissue, and the force feedback is for allowing the surgeon to know how much force he is exerting. So how the surgeon would if you have both at the same time, how the surgeon would know which one he's sensing?
Okay, that's a good question. I mean, one of the issues, and that is an issue that came up when we first started doing this. And so we had to make a distinction between tactile sensing and force reflection. And the distinction came from the way that we showed the result of the tactile sensor, which was through a pressure map at the same time as the actual palpation that was being done. So what we tried to do was to kind of emulate the way that we, as humans, make contact and we feel force. So we have both kinesthetic feedback and tactile feedback that we interpret through sensory motor integration in the brain. So there is tactile feedback that we feel from the tactile sensations in our fingers, for instance, and we feel the forces through the muscle movements that when we apply the force. So there is a distinction that we make intuitively. I mean, this is something that children learn how to do. But the way that we tried to do this was to kind of give an impression in the mind of the clinician using it that there is a map of your tactile sensation that allows them to adjust the force that they apply. So they make this distinction by looking at the pressure map, that map of the color map that we see, that's superimposed on the visual image that they see, that's sent back from the camera that comes from the surgical robot.
So okay. Basically, the modality that you're presenting is different.
So the modality, the instrument can measure both the tactile through the tactile sensor and the force through the force sensor that's attached. But the two are then integrated by the surgeon by looking at the tactile map and feeling the force that they're applying. So when they apply force, they see what effect it's having. So the two are related, because when you apply more force, the tactile map, the pressure map changes, right? And that's what we do. For instance, when we press down hard on a hard surface, we see the pressure changing. So we are correlating the force we are applying, that's the muscle force we are applying, with the tactile sensation we are feeling. And what we tried to do was to give that kind of an image to the surgeon as well. So when we asked the surgeon to do palpation, for instance, we said, when you apply force, make sure you look at the pressure map as well. So both of them are shown at the same time to the surgeon. They are on the same image.
I see.
Okay, like the bar chart, the force that they're feeling, and the pressure map are they are seeing at the same time.
It's not like a sense in their hand. It's mainly a visual representation of the force.
Yeah, I mean, but that is also reflected to some extent in the way they press down. So the pressure, the force map they get, to some extent, it also includes the pressure information. Okay. Yeah.
Other questions?
I have another question if no one has.
Okay, no problem.
Can I ask?
Sure. Yes,
Sure, you go ahead. I see one in the chat box, but I'll read after you. You can go ahead.
Sure.
So you mentioned that with inserting force sensors in the instruments, you get flexibility issues and stability issues. So my question, I assume that your 7 degree of freedom haptic feedback is translational, torque, and the grasp, if I'm correct. And then if you put the sensor on top of the instrument, why should it cause flexibility issues?
Well, the sensor doesn't cause flexibility issues. The issue is caused by the instrument itself. So if you have a thin, let's say you take a needle, you push the needle into muscle, into fat, etc. The needle actually flexes, depending on forces that are acting on the tip of the needle or along the needle.
Mm-hmm.
So when the needle flexes, that flexing has an effect on the stability part of the system, because that flexing actually means that any force you apply at the base of the needle will have to compensate for the flexing of the needle before it actually gets to that. So there's a little bit of a delay there. And for work that we have done and lots of other people have done, is that this kind of flexing, in a sense, introduces a kind of a time delay in the system. And if you think about, I mean, to look at it more, and to exaggerate this more, think about a catheter, which is very flexible. Like, let's say that you have a piece of string in your hand, and you want to position the other end of the string somewhere. And by moving this part, when you move this part, it takes a little bit of time before the other end moves. That's a time delay. And if you take this to the limit, there's a time delay even in a very small flexing part.
Mm-hmm. So
okay.
By stability, you mean that how accurate the system moves, right? The time delay will result in some inaccuracy.
Yeah, and that inaccuracy, when it's fed back, can build up.
I see. Thank you.
Right, and then as it builds up, the system will get less and less accurate, and at some point, it'll be unstable.
Thank you very much.
So Bijay has a question in the toolbar, in the chat box. Rajni, I'll interpret the question. The question is for robotic-assisted suturing. Has it been applied in practice or still in research?
Well, the work that we did was, at the moment, it's still in research now. I don't think anybody has actually used it in a clinical setting. Because
so for example, Rajni, in Davinci, I'll combine my question as well. In Davinci system, do they have automated suturing capability already?
No. No.
So how far are they at the moment?
Well, at the moment, there's still research being done. I mean, there's a group at Hopkins that did some work, and there's also a group at this hospital, Children's National Hospital in Washington. And there's some work also done in a research project at Intuitive, where they have tried to automate some aspects of suturing.
Mm.
But one of the difficulties is that it tested with AI-based automation, autonomy in suturing. The question is the data that you need to collect.
Right.
And that is one of the biggest stumbling blocks here, because there's quite a lot of variation between experts who do suturing. So while they do the same tasks, people have certain quirks in the way that they hold instruments, a certain way they tie knots and so on. So, but this is something that we are also looking at. but I haven't seen any case where it's commercial, it's used in any commercial device in an actual clinical setting.
Mm-hmm. So Bijay, that answers your question. Will come in future. So people are still working on it.
Yeah,
So,
in fact, that some people, there are cases where, especially the work at Hopkins, they've done quite a lot of work in getting almost there. The question really is the data that you need, and a huge amount of data and the training that you need for the robot to be able to do this. But there is the setup that we have at the Davinci called the Davinci Research Kit. There are lots of groups involved. U of T through SIGIT is involved in that. There are also people at a number of other places, UBC and so on, who are looking at various aspects of autonomy. And they've created an environment where they'll be sharing much of this data that people are collecting. And so that this will move much faster now that a lot of people are working on it and the data is becoming generally more widely available.
So Rajni, the Davinci system, as far as I know, at this moment still doesn't have force sensors integrated. Do you know what the company is working on in terms of that?
Well, the last time when I talked to people at Davinci, with Intuitive, basically the main problem really is how do you sensorize the instruments? And what we've shown is one way of doing it, but it's by no means a foolproof way of doing it. Optical force sensing has its own problems because FBGs, as you know, are sensitive to temperature variations.
Right.
And to calibrate this and they can be sterilized, but to create an instrument that's sterilizable, can be calibrated accurately and all that, those are major issues that need to be addressed. Intuitive is interested, but for the most part, they are hesitating on putting something like this, I think, because of the difficulties with doing this.
I see.
And I think one of the things that we have noticed in the work that we have done is poor haptic feedback is much worse than no feedback at all.
Right.
Okay.
That's well said. Yeah.
So I think people hesitate in providing this, but what we have shown is that when haptic feedback is good, then it can significantly improve performance. Now there are some cases, some robots, not necessarily this kind of surgical, full-scale surgical robots like the Davinci, but there are some robots where there is force feedback available. So there are robots, for instance, in doing in some kind of endoscopy robots where there's sensing provided as well. So for instance, in colonoscopy, there are robots that can do force sensing. So those are possible. But the kind of surgical environments you're talking about with suturing, that's not as wide as commercially available as yet. But it will be fairly soon. So there are people who are looking at specific kinds of robots with specific applications, not the general purpose robots like the Davinci. Right.
So Rajni is already 12:10. I'll ask you one last question.
Sure.
I think it was controversial to all students. A short while ago, there was a heated debate in the robotics community about the terminology master and slave. And what is the final wording terminology people agreed upon? Do you know that?
Well, I mean, the one that I'm familiar with is the discussion that was held by the IEEE Haptics Society.
Yeah.
And there the consensus was to drop the master-slave term. And that's why I use leader-follower term, which I find a little bit better than master-slave. But the other term that some people have used is primary-secondary, which is to some extent less informative as opposed to leader-follower.
So there's no final consensus yet, right?
Now the consensus is that they want to get rid of that term master-slave as much as possible. So most of the papers that I've reviewed over the last year or so have generally used leader-follower as the term. But unfortunately, the other term is not going to die out completely because it's so well embedded in the system that it's very difficult for people to think in any other term than that.
So to our students, let's do leader and follower. So,
I
so
think
you
leader
can
follower
avoid the
is one that
controversy.
I'm asking my students to use in their thesis or in their papers. And a lot of other people who are part of the Robotics and Automation Society are also following that.
That's right. In Robotics Automation Society, there was a very heated debate as well. I think a leader follower was agreed upon by most people, but not all.
Yeah. So I'm perfectly comfortable with that. And I think that kind of conveys the message easily and basically what we want to say. So I don't have a problem with that.
Anyhow, Rajni, we took a lot of your time today, and
No problem at all.
on
It's
behalf
a
of
pleasure.
the class, thank you very much again.
And I'm sorry I went over the time. I didn't realize that I was talking too much, especially when you don't see. One thing is in this kind of Zoom environment, when you don't see the people's faces when they get put off, you tend to go on and on and on.
So, you'll rarely see so many hand clapping given to our invited lecturers in this class. And also our students, I think, are good enough. I got 4 of them who turned on their cameras, so which is quite good.
Yeah.
But thank you, Rajni.
Okay, you're most welcome. Thank you.
Yeah,
take care.
Yeah, bye-bye.
Bye, everyone.
To our class, this is our last lecture for the semester. I need to thank everybody to take the course. And I also need to thank Kimberly in particular and Holly for coordinating everything with me. It was a lot of work inviting great lecturers and coordinating time. And I thank them again for the efforts. And I thank you for taking the course and auditing the course. I hope you learned something throughout the semester. And I look forward to seeing you on campus, hopefully soon.
Oh,